Next part will be to show feasibility, right? So B, let's look at feasibility. Okay, I'm going to draw this once again. Grad C1, this is my X, okay, this is my grad F, this is my S, this is I'm not going to draw this now, we'll just keep this as a way. All right, let's take some point over here, W belonging to A. Okay, so I'm going to use a second, again, intuitive property of convex sets without proof. Okay, and what is that? If so S is on the boundary of this set because it's arrived at by projection. Okay, so if I take, let's use blue. If I take this point S and join it to a point in the interior, so for example W is a point in the interior, I take this, okay, and I connect S to any point outside the convex set here, for example. Okay, what is this vector that I've just drawn over here in the bottom vector? So it's not S minus grad F, but grad F minus S, right? So this guy is grad F minus S. Okay, so the question is, will this angle always be acute, 90 degrees, or obtuse? It's a convex set. Maybe draw some things in your mind. So it's a convex set. That means, so for example, this is a convex set, right? On the other hand, this is not a convex set, right? So now, given that we have a convex, given that A is a convex set, this angle between a boundary point and an interior, and boundary point at any point outside, has to always be obtuse, right? You can see that in the second example over here, I can imagine that some angle can be acute, but if I am always like this inside a convex set, okay, I am not proving this formally, but you can arrive at it intuitively, this angle will always be obtuse. Okay, so what are these two vectors? I have, okay, so this vector that I have drawn on the top, is it S minus W, W minus S? W minus S, right? What is the quick way to remember which way the vector points? The destination is the first guy, the source from where you started has the minus sign. So I will get that W minus S inner product if I take with grad F minus S. What should this be? Less than, right? This should be less than or equal to 0. Okay. So once again, as I said, this is without proof, but at least geometrically you can get a good idea about it. Okay. So we've just written this down. W is up to us for us. It's up to us. We can choose W in any way that is convenient for us. Agreed? So let's just flip this around. Because the whole entire claim that we made was about S minus grad F, and here I have grad F minus S. So if I multiply a minus sign, I have to flip the inequality. So I'll just do that. So W minus S transpose S minus grad F is greater than equal to 0. Okay. As I mentioned, W is up to us to choose. Okay. So say we choose W is equal to S plus grad C1. S plus grad C1, will that still be in A? Clearly, right? Grad C, in fact, in this example, grad C1 and S are along the same line. So I'm going to be, so therefore W, I have chosen a legitimate W. It belongs to the cone A. Okay. So if I choose W in this way, what happens to my inequality? First term becomes grad C1, right? That's all that is left. W minus S is equal to grad C1. So this becomes grad C1 transpose S minus grad F greater than equal to 0, right? Fine. We can continue this logic. Supposing we choose, what should I choose? S plus grad C2. Is this again legal? Does it belong to A? Right? You can see S is along grad C1 and grad C2 is there. If I take their conic combination with coefficients 1 and 1, I will still be in the set A. So this also belongs to A. So that gives us what? Grad C2 transpose S minus grad F greater than equal to 0. So together, what does this imply? If you look back at what we had wanted, right? We had said we had made a claim of feasible and descent direction. We already showed it is descent direction. And here we are showing that grad C1 transpose D greater than 0, grad C2 transpose D greater than 0. Therefore, S minus grad F is feasible. Which again I'm just repeating myself. This implies that S minus grad F, or rather going along S minus grad F will give me a better point than X, implies that X is not a local minima, right? This contradicts point 1 of the KKT theorem, okay? And therefore, our starting proof by contradiction follows through. Therefore, grad F belongs to the set A. We have shown a contradiction. Okay. So you notice that this is the reason why this is called a proof sketch. We did not assume anything particular about grad C1 or grad C2, right? We did not say that, oh, this proof follows only because grad C1 was minus 2x1, minus 2x2 or blah blah blah. We just used it as a framework for us to visualize this, and I chose 2 constraints. Why? Because I can draw it on a plane on the screen. If I had chosen 3 constraints or n constraints, it's very hard to visualize. 1 is too easy, 2 is the best, right? So that's why this is a proof sketch, and we have shown it for the case when both the inequalities are what? Active, inactive, active, right? So for the other cases, the proof will follow a similar kind of a logic, except that steps are simpler, okay? So I'm not going to do the proof for B, C and D. They are much simpler than this, but this is the logic that you would have to apply to arrive at it. Actually for B and C, D is just like unconstrained optimization. We don't have to, the constraints are inactive. They are not playing any role in this thing. So that part can be skipped, okay? So we'll just write this, the rest of the cases can be done. So I'll recommend try B or C as exercise, okay? This will give you good practice in also making sure that you've understood this, right? Any questions on what we did? Pretty straightforward, right? The only things you kind of had to take on faith are two slightly intuitive properties of convex sets. The first property was what? The length of the projection is less than the less than or equal to the length less than the equal to strictly less than the length of the original vector, and strictly less because I said grad f does not live in A. Okay, that was the first assumption, and the second assumption was about the angle subtended between an interior point and a exterior point. This angle is obtuse. Okay, that also by drawing a few sketches you can convince yourself that that is true. Okay, so let me just make that note over here, otherwise later you'll wonder what that is. So convex, not convex. Okay, and that gave us feasible and descent directions. Okay, so to make sure that we really understand this, I'm going to take a couple of examples. So we'll work through a couple of examples. First, one example very similar to what we have done. The second is a totally different example, and that will give us some practice. Okay, so we are going to continue with the same problem. Okay, f of x is x1 plus x2, and c1x is 2 minus x1 squared minus x2 squared is greater than equal to 0, and c2x is equal to x2 greater than equal to 0. The same problem. Okay, and we're going to use this KKT theorem as a tester, right? So we will give it a few points and we'll see how to use the KKT theorem. Okay, this is your sort of first experience in given a theorem, how do we use it? Okay, so let's take, okay, I'm going to take 2 points, point A, which is minus 1 comma 0, and point B, which is minus root 2 comma 0. These are the 2 points, and we will subject our points A and B to this test. Okay, so let's take point A. Okay, you can also write down grad C1. That's pretty straightforward, and grad C2 is simply 0, 1. Okay. At point A, let's go step by step. Let's list out what are the, you should always list out what are the active and inactive constraints, because that helps us to figure out which Lagrange multipliers to worry about or not. So at point A, which of the constraints are active? Right. So if I do C1 XA, what do I get? Substitute this coordinate inside, what do I get? 1. 1 is strictly greater than 0. C2 XA, what is it equal to? 0, right? So this is equal to 0. That means this is active, this is inactive. Okay. Can I say something about lambda 1, lambda 2? Lambda 1 has to be 0 because of complementarity conditions, right? So my grad f, Lagrangian of x lambda is going to be f minus lambda 2 C2. Why? Because lambda 1 is 0. Okay. Now, is this an optimal point or not? If XA is optimal, this is the point number 1 of the if condition of the KKT theorem, right? We have to say is XA, it says that if XA is optimal, then everything else is going to follow. F and C are differentiable, all of that has happened, okay? grad C1, you can see grad C1 and grad C2 if you substitute, that will, is LICQ being satisfied? Yes, why? What is grad C1? 2, 0, grad C2, 0, 1, are they linearly independent? Yes, LICQ is satisfied. So, point 1, 2, so 1, 2 and 3 are satisfied. Now, let us see the then part, right? If Xi is optimal, we should have grad Lagrangian equal to 0, right? So, then let's write that grad X Lagrangian equal to 0. So, grad F must be equal to lambda 2 grad C2. This must hold true, okay? What is grad F? F is here. What is grad F? 1, 1, right? So, this is 1, 1 should be equal to, and grad C2 is sitting in front of us, 0, 1, 0, 1, okay. So, if XA were to be an optimal point, we should find a set of Lagrange multipliers such that grad L equal to 0 holds true, right? For this to hold true, is there any value of lambda 1 and lambda 2 that will satisfy this? No. Do what you want, 1 is equal to 0 can never be satisfied. So, implies no value of lambda 2 works, right? Since I cannot find any Lagrange multiplier over here, this is where my test works, right? So, this says that XA is not optimal. This is how you use your KKT theorem. You subject your point to the test says grad L should be 0, complementarity conditions blah blah, but for grad L to be 0, I am not able to come up with a lambda 1 lambda 2 that does it, therefore fail, okay. Let us look at point B. What is C1 at B? What is B? Minus root 2 comma 0. So, therefore, it's on the corner over there. So, C1 is 0, C2 is equal to 0. That means both are active. If both are active, can I say anything about lambda 1, lambda 2? They need not be 0, right? So, I would then have to have grad F should be equal to lambda 1 grad C1 plus lambda 2 grad C2, okay. We have to find, are there such lambda 1 and lambda 2 that solve or satisfy the situation? Let us see. So, I get 1, 1 from grad F. Why? Because grad F is x1 plus x2. So, grad C1 at xb, what is its value? Lambda 1, what do I write here? 2 root 2 comma 0 plus lambda 2 is all, grad C2 is always the same, which is 0, 1, right. So, does that give me a value for lambda 1 and lambda 2? Yeah, straight away, lambda 1 is equal to 1 by 2 root 2, lambda 2 is equal to 1. That's not enough. What further thing do I have to check? I found a set of lambda 1 and lambda 2 that satisfy grad L equal to 0. What were these constraints? Were they equalities or inequalities? Inequalities. Therefore, there is a further stipulation on the Lagrange multipliers. They should be non-negative, right? Are they non-negative? Yes. So, I have to make sure that, because if you reach till here and one of them is negative, you are finished, right? So, finally we should make note of this, lambda 1, lambda 2 are this. Therefore, to first order, XB is a optimal point. Satisfies KKT, therefore optimal point. So, everyone's got the logic that we need to follow over here, right? You verify points 2 and 3 of your if condition. They are satisfied, proceed to the implications of this, right? And if it works, then you have found a point that satisfies, okay. So, you can see this is also quite easy for you to code up, right? You would have to have some way to solve for lambda 1 and lambda 2 and then check, does it exist? Is there a solution to this system of equations? And it's actually it's a very simple system of equations to solve. Is it a linear system of equations to solve? It is, right? Because I can write this as I could write this as grad C transpose lambda, right? This whole thing I can write in a compact way like this. Grad C transpose with lambda is lambda 1, lambda 2. I can solve for lambda using any numerical technique and then see what is the solution I get. Is there a solution? Is it positive? All of that. All of this is satisfied and I can say, okay, to first order, this guy passes the test. It satisfies the KKT condition. Okay. So this is really one of the most foundational bedrock theorems of constraint optimization, the KKT conditions. Okay. I've mentioned this previously. You will come across this theorem in the books sometimes with a sign flipped. The Lagrangian will be defined as grad f plus lambda 1 plus lambda 2 etc. So all the signs will get flipped. Just make sure you know what is the starting point before you get confused by the subsequent results. Okay. This is clear?